Here's a sample of pulse width modulation on the oscilloscope. We're using the Arduino with a simple little analog input and output program to generate a pulse wave modulated signal. Right now we're not putting out any signal at all. It's 0 volts. As we start to bring our potentiometer up, we begin to send out a little pulse, and as we keep turning it up, it's a little wider pulse, and there we have about a 50% duty cycle. And back here we have about a 25% duty cycle. You can see it goes up as we turn our potentiometer. 75% duty cycle. That's the time that the pulse is on in a high condition as opposed to a low position of 0 volts. And then we have 100% duty cycle, or 5 volts is running straight through, so we're on a switch. Now the beauty of this is that we can vary the width of that pulse and use that varying pulse to control things like motors, motor speed, and the intensity on LEDs, which sometimes is handy to have a brightness control. So it's very useful. Just a little information on how the scope is set up. From the lower trace to the upper trace, we're representing the voltage of the signal. Each one of the little squares or gradations is worth 2 volts. And you have a knob over here to set that. You can vary that. But if we count those up, we've got 2 volts here, 2 volts here, and about a half a volt here. A little less, but close enough. So we've got 1, 2, 3, 4, 5 volts from peak to peak. That's called the peak-to-peak voltage. From a minimum of 0 all the way up to our 4.8 or 5 volts. Then back down again according to the duration of the upper peak, which is our duty cycle, which we talked about a little bit ago. The duty cycle is how long the peak is at the top compared to when we're at the bottom with no voltage. And the other axis represents time. This is time as that wave travels across the universe. In time, we're at 1/2 a millisecond per division. So each division is a 1/2 millisecond. 2 of them is 1 millisecond. 3 of them is 1.5 milliseconds. 4 of them would be 4 milliseconds. Now you note that if we want to check the period of this waveform, the period is the time it takes to get from one place in a waveform to the exact same place in the next wave. And we'll measure that by starting at the peak here to the peak of the next one. We have 1, 2, 3, 4 divisions, 4 gradations. We know that each one of those is 1/2 millisecond each, so that gives us a total period of 2 milliseconds. If we want to express that in frequency, the time per second frequency in hertz is actually the cycles per second. They mean the same thing. So we use that measurement a lot to express the characteristics of a waveform, and we'll say that the frequency of that in this case would be 1 divided by 1,000 divided by 2, which gives us 500 cycles per second, or 500 hertz. I think you can see the relationship between those different measurements. So as we vary the width of the pulse, we're sending more and more current to the output as we increase it, and as we bring it back, we're decreasing the current until we're back to 0. And we'll show you what the effect is on the LED when we do that. Here's the test circuit that we're using. You just saw what representation of what we're doing on the oscilloscope, a very useful tool. Here's our potentiometer, 10K potentiometer, which we will change the duty cycle of our wave. And at this point you can see the LED at the right, which is tied to the output. As we decrease the duty cycle, you can see that LED go out. We're now at 0 volts. And as we increase it slowly, you'll note we get more and more brightness as we go on up to the point where we have a 100% duty cycle, or a full 5 volts across the LED. And actually it's a little less because we have a current limiting resistor in line with it. But you can see the usefulness of it in order to dim an LED. And that's being done not by varying the voltage, as one might think we would do, but by varying the time the voltage is on as compared to the time the voltage is off. Switching it on and off very, very rapidly at 500 times per second, which is our frequency, and with different amounts of duty cycle from 0% to 100%. Now we'll stick a motor in line and we'll take a look at that. We've changed our test setup here slightly to drive a little motor. This little tiny motor here, a hobby motor, got a gear on the end of it for some other project we had one time. But we had to modify our setup a little here because that motor requires a bit too much current to be driven directly from the Arduino PWM digital pin. So we're employing a little device called a UNL 2003A. It's an IC here that's really a series of some Darlington pairs, and we hooked a few of them in parallel to get enough current to drive that motor. But we'll run our PWM, our pulse width modulated signal, into the input of the 2003, and the output will then will provide more current, and it'll drive our motor for us. We're using an external power supply. We have that set at 5 volts. It's a 3-volt motor, but it'll take 5 all right. We can set her down a little slower too, but you'll get the idea. And we still have our potentiometer to widen the pulse. You can hear our motor take off. We'll see if we can get that on video for you. Okay, should be looking right at it here. So I turn the pod up. We have no PWM signal at all now as we start to get into it. Notice how nice and slow and smooth the motor starts. This is a lot of the transformers on your HO model railroad trains setups will use PWM nowadays because it provides a more precise control of the motors and the engines, and they run a lot smoother. We're really working with average voltage, average current in the PWM. And we'll drive it with our CPL signal. We're really shaking that baby around now. Alright, now we'll show you the waveform. We're still hooked up to our oscilloscope. So we can do this. Turn it with one hand and hold it with the other. Alright. Try and get rid of the reflection. There's our pulse starting up. We'll increase the duty cycle. You can hear the motor going as we do that. The more the duty cycle it gets, the faster she goes. So we get to the point where we got a solid 5 volts delta. And we're modifying that with our power. And as we speed up, the pulse on the scope is a little unstable, but that's because we're getting some back EMF. Motors are very noisy devices, and it's generating a lot of noise that gets into our back circuit there and causes the oscilloscope a little bit of difficulty in triggering, but you can get the idea. Notice as try to hold this up to get rid of that reflection. Notice as the pulse width increases, the motor will slowly start. I get to the start threshold, and it will continue to gain speed and torque. Actually, low speed will but you always have a lot of torque, a lot more torque at the lower speed than a gasoline engine does. There we are, 100%. Okay. Another thing to take a look at is that's not a real fine current adjust, the right hand 2 digits, but you'll see the current as it speeds up. The motor is using will pop up to around 0.1 milliamps as it starts. This may go on to around 200 milliamps. Yeah. So that's that. Shows you how that works. All right.